Hey, today we're going to talk about Taylor polynomials. Now, unfortunately, this set of notes is not in section 10A that I gave you already or 10B that I gave you before we left. This one's kind of on its own. So I have uploaded a PDF. You can print out the pages that you need to copy notes on, or you can mark up the PDF. Either one works. Actually, the app that I downloaded is called Notability. I think it's about $7. There are other ways to mark up PDFs out there. I know you can do it in your notes, but this one seems to be working pretty well for me. So if you search around, you'll find something. We've actually already discussed differential equations. We've talked about slope fields. We've talked about, this was Euler's method, the logistic equation, that's the exponential growth that goes up and levels off. We've talked about all of those. Today we are looking at Taylor polynomials. So at the end of this lesson, after the notes, I'll ask you to do page 509. Those are these problems. Tomorrow I'll have you do worksheet 8.4, and that's also uploaded as a PDF that you can work on another piece of paper or mark up the PDF. On this page are the answers that are uploaded. So you'll be looking at this set right here. I'll have to go look through some of these problems as I'm looking at these answers over here. Those are error problems, and I don't think we need to know those, which is actually really, really good news. So here we go. Section 8.4, Taylor polynomials. We know how to approximate a function by a tangent line. So what we can do is we can take any function in the world, we can zoom in really, really close and find a tangent line. So that's what's going on in this picture on the top of your notes. Here's my curve that's in blue, that's my function. That magenta, or that red color, is the equation, or is the tangent line. And the closer and closer and closer you zoom in fact, I can zoom in on my picture, the closer that function starts to look like a straight line. So right there, the blue, it does curve, but it's closer and closer and closer to that pink or that red line. So we've done that before. Now, Taylor polynomials. You can now approximate a curve not with just a straight line, but with a polynomial. And when we say polynomial, that should take you back to Algebra 2 and pre-calc. A polynomial is a parabola. So there's my parabola. Or it's a cubic function. Or it's something to the 4th power. Or it's something to the 5th power. And then depending on all those other terms and the exponents and your coefficients, you get those other loops in there. So it might look like this. It might look like this. Whatever it is, we can now approximate one function with another function. You're kind of wondering, well, why on earth do I need to do that? It's especially helpful with your e to the x, your trig functions, your natural log of x. Those are called your transcendental functions. So they're not nice, neat functions. They do work, but sometimes the math is easier with a polynomial if you just have x terms as opposed to a trig function or an e or an ln. So what I have for you is a definition. And this is the tangent line approximation at x equals 0 is the first Taylor approximation. So here, this last piece, that's my approximation. So the function is the function evaluated at 0 plus f prime of 0 times x. It's really nothing more than the equation of a line, if we're talking about a line right here. Let me zoom in. There we go. We have y1 plus, here's my slope, x. And this y1 is really your b. So it's really y equals mx plus b. It's just a line. We've talked about lines for a very, very long time. So here we go. Example 1. Find a Taylor polynomial of degree 1 for g of x equals cosine of x near x equals 0. You want to be organized with your work with these. So we're going to start with our original function. G of x is equal to the cosine of x. Okay. The other thing that we need is the derivative. So g prime of x is the derivative of cosine, and the derivative of cosine is negative sine. And we need to evaluate these near x equals 0. Those are really nice. Those are the best ones around x equals 0. So later on, we'll talk about Taylor series and then Maclaurin series. The Maclaurin series is just a Taylor series centered at x equals 0. It's a good thing. So you want to find g of 0, which is cosine of 0. And you also want to find g prime of 0, which is negative sine of 0. So think back to your unit circle. Cosine of 0 is equal to 1. Negative sine of 0 is equal to 0. So this is all your side work. So you want to keep that nice and neat and tidy somewhere. And then you have to put it into the formula. So my Taylor polynomial is f of 0 plus f prime of 0 times x. Now x is just x, it's a variable. Please don't be putting zeros into that. Let's give ourselves a little bit more space. My Taylor polynomial, 1 is my degree 1. So f of 0 we already figured out on the left is a 1. Plus f prime of 0, in this case f is g, g is f, they're the same thing, is the slope, which is 0, times x. So a polynomial of degree 1 is equal to 1. You don't have to include that 0x. This is my solution. Oh, what are you doing, Mrs. Charlie? What are you talking about? So let's hop over here to Desmos. I hope this works. So we are trying to approximate y equals cosine of x. Now you can do this on your calculator. I just figured it was easier on Desmos to hop back and forth on my iPad. And what we did was we approximated that with y is equal to 1. So what I'm saying is, all right, we're really, really, really close to 0. And at x equals 0, my cosine curve, that red curve, can be approximated by the line y equals 1. So yeah, if I look up here, that's true. No, I can't highlight to show you guys that. But that's pretty true. All right, let's go back to our notes. Well, that doesn't hold very true further out. So we need more terms. And that's what P2 is. Let's calculate this to a second degree. So here's my formula now. I see I have a typo. This should be a 0. So now to find the second degree Taylor polynomial, we need f of 0, we need f prime of 0, and we need the second derivative at 0. Because here's the original, first derivative, second derivative. We need all three of those things. So f is still that original function, which is cosine. So we're talking about cosine of 0, which is 1. F prime of 0 is the derivative, so that's negative sine of x, so negative sine of 0, which is 0. And then the second derivative, so now I need the derivative of negative sine. So the derivative of sine is cosine, but it's still negative in the front, so this is negative cosine of 0, which is a negative 1. So now we take those pieces and put them into our formula. So P2 is f of 0 plus f prime of 0 times x plus f prime of 0, that should be 0, times x squared over 2. Now, I'm going to show you where all these pieces come from on the next page, but right now we're just filling in the pieces. So my second degree Taylor polynomial means I could have up to exponent 2 is 1 plus 0 times x plus second derivative at 0 is negative 1 times x squared over 2. So that's filling in the formula, but if I clean this up a smidge, second degree Taylor polynomial is 1 minus x squared over 2. Well, now I've gone from 1 to 1 minus x squared over 2. So let's go graph this and see what it looks like. So my next one. y equals 1 minus, we said x squared over 2, right? X squared divided by 2. All right, now we're talking. So the red curve, in fact, let's make that a different color. Let's make that black. My original curve is cosine. Now, y equals 1 was the first approximation that we did. Y equals 1 minus x squared over 2. That's my second approximation. So if this black curve is the original cosine, the blue was my first estimate. Well, now I'm looking at the green. Now we're getting somewhere. That green does actually start to follow the cosine curve. Now it fails the further away you get from 0, but when you're pretty close to 0, yeah, I can see it. That green curve does follow the black curve. That's what we're looking for, those Taylor polynomials. We are looking to approximate another function. So great job. So where are all these crazy formulas coming from? Here they are, my friends, my Taylor polynomials. This is the next page. For a better approximation, you need a higher degree polynomial. This is the formula. It looks overwhelming at first, but it's really, really not. It really is not too scary. This is the function evaluated at 0, the first derivative times x to the first, the second derivative, x squared over 2 factorial, third derivative, x cubed over 3 factorial, fourth derivative, x to the fourth over 4 factorial. And it keeps going and going and going and going, and here's your n. So where's the last place we saw things that kept going and going and going to n? Series. So there is a connection between these Taylor polynomials and Taylor series. I'll give you a lesson on that next. So this is the type of problem I want you to know how to do. Construct a Taylor polynomial degree 7 for sine of 0 near 0. Now, I see I have a typo here as well. You should say sine of x. Make that an x, not a 0. One of these years, I'll have all these typos figured out. So again, be neat and tidy in your work. It doesn't matter if you list these out vertically or horizontally, it's up to you. But if we are going to 7th degree, then we need 7 derivatives. So here's my original. I'm going to start with f of x. Is sine of x. And the first derivative of sine is cosine. And the second derivative is negative sine of x. And the third derivative is negative cosine of x. And the fourth derivative is, the derivative of cosine is negative sine, but it's already negative, so this will be positive sine of x. And the fifth derivative is cosine of x. And the sixth derivative is negative sine of x. I know this feels silly. And then the seventh derivative is negative cosine of x. Let me just double check my work real quick. We're good. So we've evaluated, or excuse me, we haven't evaluated them. We found all these derivatives. We're up to the seventh derivative. Now we need to evaluate them all at 0. If I'm centered around 0, I find the value of these derivatives all at 0. So instead of rewriting all of these out, so I'm going to say over here at x equals 0. I'm going to cheat on the function notation a little bit. So sine of 0 is 0. Cosine of 0 is 1. Negative sine of 0 is 0. Negative cosine of 0 is negative 1. Sine of 0 is 0. Cosine of 0 is positive 1. Negative sine of 0 is 0. And negative cosine of 0 is negative 1. So now we've evaluated all of these derivatives at 0 all the way through the seventh derivative. Our job is to put the rest of these into this formula. So here we go. What does this whole thing look like? My 7th degree Taylor polynomial is going to be the original at 0, which is 0, plus the first derivative times x, so it's 1x, excuse me, plus the second one, which is 0, times x squared over 2 factorial, plus the value of the third derivative, so I've got a negative 1, x cubed over 3 factorial, plus 0, x to the 4th over 4 factorial, plus 1, x to the 5th over 5 factorial, plus 0, x to the 6th over 6 factorial, plus, run out of space, a negative 1, x to the 7th over 7 factorial. So I know this looks crazy and I ran out of space across the page here, but here's the good news, we have a lot of zeros. So the 7th degree Taylor polynomial, we can drop all the terms that have zeros, is 1x minus 1 over 3 factorial x cubed. The next term is 0 plus 1 over 5 factorial x to the 5th. The x to the 6th term is gone, so minus 1 over 7 factorial x to the 7th. Now, I have seen answers left with the factorial there, but not always. So I don't know what that final answer is. Can we leave the factorial? Yes, I think sometimes you can. What will the expectations be on this year's exam? I don't know. So it doesn't hurt to turn those into numbers. Remember, if 3 factorial means 3 times 2 times 1. So that's pretty easy by hand, 1/6 x cubed. 5 factorial is 5 times 4 times 3 times 2 times 1. So 5 times 4 is 20, times 3 is 60, times 2 is 120, times 1 is still 120. So plus 1 over 120, x to the 5th. Now 7 factorial is not happening in my head this afternoon. So in my calculator, it does exist. It's under your math button, probability. Math probability, number 4. So 7 math probability, number 4. So 7 exclamation point, might be able to find it faster, is 5,040. Okay, there you go. That is our 7th degree Taylor polynomial to approximate sine of x near 0. What you doing, Mrs. Trinley? What does this look like? So let's go back to our graph. Let's switch it up a little bit. So we don't want this one anymore. We don't want this one. We're not talking about cosine anymore. Now we're talking about sine. Type this in here. Too many x's. All right, we can handle the extra parentheses, that's fine. Okay, so what did we approximate this with? Well, we approximated this with y equals, now back to my other page, 1x minus 1/6 x cubed, x minus 1/6 x cubed. Hey, those match pretty closely in the middle, but let's get some more terms on there. Plus 1/20 x to the 5th plus 1/120 x to the 5th minus 1 over, it's 5,040, I think, x to the 7th. All right, there we go. See, this is where I think these are really, really cool. Now that I have a polynomial to the 7th term, look how much of that matches your sine curve. That's really cool. So the blue curve and the black curve overlap completely. Let's change the color on this just so you can see a little bit better, a little more contrast. Oop, better turn it back on. There you go. They completely overlap when you're close to 0. Look at that. They completely overlap. And the further away you get, that's where they start to extend. And so there's a piece that we're going to miss out on. Maybe after the AP exam, we'll talk about this. You can see, well, how accurate is your Taylor polynomial? Just how far do they match? So if I'm looking at round numbers on this one, this is a guess, nothing mathematical here. It looks like from the bottom, from -1 over here, as my low up here to a +1. Yeah, it looks like that matches all the way through there. What is -1.57? Is that pi over 2? It's pi over 2. So it looks like from negative pi over 2 to positive pi over 2, they match. And you can see, well, how good is your estimate? What's your error? So in this case, the closer we are to 0, the more accurate it is, the smaller that error is. Now, if I'm over here at 4, yeah, it's looking pretty shady. They don't match. There's a big difference between the black curve and the orange curve. Now you've got a real error and it doesn't make sense anymore. In fact, the further away you get, yeah, that orange curve doesn't match your sine curve anymore. So you're always looking at really, really small intervals for these to match. But the math is easier a lot of times with polynomials than it is with those transcendental functions. That's what they're called. All right, what else do we have? You don't always have to be centered at 0. All right, there's error. We're going to talk about this one that's not centered at 0. You can be centered at anything else. You just have to account for the shift, and that's what you see in the formula. So it's still the original function plus the first derivative, x minus a squared. Where have you seen that before? Well, you've seen it anytime you shift that parabola. If you have a +2, shifts it left 2. If you had a -7, it shifts it right 7. So that minus a in there is taking care of that shift when you're off of 0. So let me show you what this Taylor looks like. For 4th degree, it doesn't mean 4 terms. It means 4th degree, 4 is an exponent, for natural log of x near 1. So this is where x equals 1. This is where x equals 1. So again, be organized in your work. Make yourself a list. So f of x equals the natural log of x. The first derivative, do you remember natural log? It's 1 over x, which our lives will be easier if we call this x to the -1. The second derivative is -1x to the -2. My third derivative is 2x to the -3. And my fourth derivative, because we're talking about 4th degree, is -6x to the -4th. So natural log is gone. You have all of these powers in here. Where are we evaluating them? We're evaluating them at x equals 1. So at x equals 1. So the natural log of x, or the natural log of 1, is 0. 1 to the -1 is 1. -1 times 1 to the -2, well, that's really -1 times 1 over 1. So this is -1. If I put 1 in for x in the third derivative, this is a 2. If I put 1 in for x in the fourth derivative, this is a -6. So while those negative exponents look a little crazy, because we're evaluating at 1, this actually works out very, very nicely. So my polynomial looks something like this. 4th degree Taylor polynomial is going to be 0 plus first derivative evaluated at 1, which is 1, x minus a, so it's x minus 1, minus 1 over 2 factorial times x minus 1 squared. All I'm doing is following the formula up here. It looks a little bit crazy, just one step at a time. Where am I at? Plus 2, this is the 3rd degree one, over 3 factorial x minus 1 cubed. I want to try something here to shrink all this down for us. Okay. No, I didn't really want to move all that. Let's try again. Thanks for being patient with me. As soon as we get all this figured out, it'll be official summer break, huh? Okay. There we go. Shrunken handwriting. So if I zoom in here a little bit, there we go. What are we at? Minus 6 over 4 factorial x minus 1 to the 4th. So there's your 4th degree, but you want to ask yourself, hey, can I clean this up a little bit? The answer is yes. Yes, you can. Not even just the handwriting, but you want to clean up those factorials if you can. So 4th degree, 4th, you don't want to write over there, 4th degree. So this is x minus 1. 2 factorial is just 2, so minus 1/2 x minus 1 squared. 3 factorial is 3 times 2, so that's 6. So plus 2/6 x minus 1 cubed. And 4 factorial is 4 times 3 times 2 times 1, so 4 times 3 is 12, times 2 is 24, minus 6/24 x minus 1 to the 4th. Fun times. The only other thing I would do is reduce those fractions. Now, technically on the AP exam, do you have to reduce fractions? Nope. Nope, you don't. It doesn't have to be simplified all the way. And being as we know you have 2 free response questions this year, they do not. So minus 1/2 x minus 1 squared. 2/6 is really 1/3. X minus 1 cubed. 6/24 is 1/4 x minus 1 to the 4th. So there you go. There's our Taylor polynomial. I really like them. I know, I'm a nerdy math teacher. I think they're neat little puzzles. And what you'll see sometimes, and especially on the AP exam, and these are some of the problems I pulled for Thursday, is they'll say, all right, the first derivative has the value of this. The 4th derivative has the value of this. So you don't have to find them. You just have to fill them into the formula already. Or sometimes they'll give you the formula and say, hey, what's the value of a derivative? So it does work in both directions. Now, once you copy the notes, I'm going to hang up here, end my chat with myself, and then I'm going to go look at page 509. There's some error problems on there that we're not responsible for. I don't want to go there. There's this formula that we have to use. And yeah, it looks a little crazy. Good practice on this, if you want to test yourself out, would be to find the 4th degree Taylor polynomial. Absolutely, you can do that for e to the x. The derivative of e to the x is always just e to the x. But don't worry about this error formula. It looks a little intimidating. It really does. You just have to find the polynomial. And these, oh, that's right, this is a fun table. These Taylor polynomials, all centered at 0, are called Maclaurin polynomials. But here's an e to the x in expanded form, a sine of x in expanded form, cosine of x in expanded form, and a natural log in expanded form. So there you go. Good luck. Email me with questions. Email me. From the looks of YouTube, not all of us are watching these, and that's okay, but ask me questions.